Okay, grade nines. I know we've started with, or we're actually done with this slide. I just want to use this as an introduction for the rest of the lesson. And then also, I want you guys to not slow down the lesson, rather listen. If you can't copy everything, that's fine. There is one part that I'm going to actually give you time to copy. Um, and then when the lesson is done, then you can take out your phones, turn off the sound, and make sure that everything is copied in your book so that next time when I see you guys again, your books are up to date. So I am uploading the video onto Classroom as well, so you can do that in your own time. Okay, so we were talking about forces, and we said that we divide forces into two main categories. We have contact forces and we have non-contact forces. So contact forces, we talked about two of them the other day, and we list them as friction, compression, and tension. And then the non-contact forces, we're going to start on the first one today. Non-contact forces are forces where the objects do not need to be in contact with another. They can be in contact, but they don't need to be. So we're going to talk about gravity today, and then the other two is magnetic force and electrostatic force. So this one, I think you guys copied the other day as well, so I'm just going to run through it quickly. We said tension is what the force that's in a rope if something is pulling on it, and compression is the force that is on an object that is being squeezed or pushed together like a spring. And then this one, I don't think we got to the other day, so I'm just going to stand still on this one for a while. Friction is also a type of a contact force, and it is the force that occurs when objects are rubbing against each other. The easy way to experience friction is if it's cold outside and you rub your hands together, then you warm them up. That's friction heating your hands up. And or you can take your eraser, and once you've rubbed out quite a piece of work, then you will feel that the end of your eraser has heated up due to the friction. Friction is also the force that causes moving objects to stop. So if you were rolling a ball over the ground, then the friction between the ball and the ground would cause it to come to a standstill. Okay, I actually think this might be where we stopped the other day. I have two different flags on my presentation for some reason. So anyway, okay, so just to summarize, forces can have the following effects on an object. It can deform an object. So if I crumple up a piece of paper, I deformed it, or if I smash a piece of clay, I deformed it. It can accelerate an object. In other words, it changes its speed. That's like when you throw a ball or any other object for that matter, you are changing its speed. You can change the direction of movement. So if you're playing tennis, then by applying a force to the tennis ball, you are changing the direction of the movement. Or you can rotate an object. So if we are opening a door, or if we are wringing out washing, so if you want to get the excess water out of a wet piece of cloth, for instance, and you wring it out, then that's also a rotating force causing the water to leave the piece of cloth. Okay, and then forces and shape changes. So when it comes to, remember all of this is still a contact force. When you are applying a force on an object, we get elastic objects and non-elastic objects. So an elastic object will be where the shape change is temporary, like when you have a rubber band or a balloon. So if you have a balloon and you squish it together but not too hard, the moment you let it go, it jumps back to its original shape. Same with a rubber band. Unless you pull it too hard, then it snaps. But in general, it's an elastic object. And a non-elastic object is something that the shape change is permanent. So if we are crashing a can, or if you are building something out of clay, then you are changing the shape. It holds its new shape on its own. You don't have to, like, it doesn't jump back like a rubber band or like a balloon. Then I can't remember if I gave you guys this homework. If I didn't, please do this for next time and we'll mark it. If I did, lucky you, then you have a little less homework to do because you are getting more homework today. Hi, shame. Okay. On to gravitational force. So that's on page 121 in your books. And the first thing that you have to know about gravitational force is that it is a non-contact force. It is also an attraction force, which means it is a pulling force. So remember we said forces can be pulling or pushing. So this one is a pulling force, meaning that it pulls things closer together. And you have to know that it is the force that objects have on each other due to their masses. So all objects in the universe attract one another, but the reason why you are not leaning slightly towards Jupiter at the moment is because Jupiter is very, very far away. But theoretically, it is exerting a force on you. It's just so far away that you can't really feel it. So gravitational force is larger if the mass of the objects increase. It's very important that you guys know this, and we're going to do some practical applications of this as well. And it's also bigger if the objects are closer to one another. So like I just said with Jupiter, you are not experiencing a real gravitational force due to Jupiter because you are very, very far away from Jupiter. But you are experiencing a real gravitational force due to the Earth because in fact you're very close to the Earth. If we are looking at the masses, so you are actually attracted by, let's say, the pavilion on the other side of the field, of the sport field. That object has a mass, so it is actually attracting you. But the reason why you aren't being pulled towards it is because the mass of the pavilion, even though it is quite big, is significantly, like it's so small compared to the mass of the Earth. So the only real gravitational force that we as humans experience is due to the Earth because just because the mass of the Earth is so big compared to the mass of anything else around us. Okay, so there are gravitational forces between the sun and the planets, keeping us in the orbitals, between the Earth and the moon, making sure that the Earth keeps rotating around us, and between the Earth and any object on its surface, like we just said. And that's why I quite like this picture. It shows that the sun is like holding on to all the different planets, but also that all the different planets are holding on to one another. In in some way everything is connected. Isn't that lovely? Okay, so let's talk about this. What happens to the gravitational force between two objects if they are moved further away from each other? So here we have the dark blue, let's say it's a planet, and the light blue, let's say it's a moon. But what would happen if we move the moon slightly further away from the planet? Then it will decrease, because the further they are away from one another, the smaller the gravitational force will be. Other one, what will happen to the gravitational force between two objects if they become heavier or if their mass increases? So we said that bigger mass or higher mass means stronger gravitational force. In other words, the gravitational force will increase. Okay, so those are the two practical applications. If we move objects further away or closer to, how does that affect gravitation? And the second one is if we change the mass of any of the two objects or maybe both of the objects, how does that affect gravitational force? And the questions that you are going to do for homework also touches on this. Okay. Like all forces, gravitational force occurs in pairs. So if object 1 attracts object 2, then object 2 attracts object 1. And the picture that I put there is just the Earth and the Moon. So the Earth attracts the Moon with a certain force as we are looking at it, it attracts it to the left. But the Moon is also attracting the Earth with exactly the same size of force, but the direction will be opposite. So it's attracting it as we are looking at it to the right. So Moon on Earth attracting it to the left, but Earth on Moon attracting it to the right will be exactly the same size of the force, but it will be in the opposite direction. Okay, then I'm going to attach this video as well for you guys. So this video shows a man going to NASA has a room where they can make it without any air resistance. And then it shows you that if we ignore the effects of air resistance, then all objects on Earth fall at the same acceleration, whether it be, in this case, they used a feather, and a big bowling ball, and they drop them from the same height, then they hit the ground at exactly the same time, because it's actually air resistance that slows down a feather as it falls downwards. And this experiment just shows you that if we eliminate the effects of air resistance, then a feather and a bowling ball that's dropped at exactly the same time from the same height will hit the ground at the same time as well. So what you guys need to know about gravity is it pulls an object straight downwards. It's not like you can drop a coffee mug and it's going to fall 2 meters away from you. It goes straight downwards if it's dropped towards the center of the planet, and objects fall at the same rate no matter their mass. And you guys can watch that video for a nice practical application of that. I'll ask the teacher to show you guys. And then this slide is very, very important because we have to know the difference between the mass of an object and the weight of an object. So what I'm actually going to do is I'm going to stop the video here, and you guys can pause it and take some time to just copy that in your books. And then if you don't want to, you can always go and do it at home when you rewatch the videos. And then I'm not going to discuss it in the next video.